we shift gears dramatically from heat engines into chapter 23. Chapter 23 is the last of the 3 chapters that you'll see on exam 2. That's all here. Here's all of the homework. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 chapter 23 problems. Just know what it means to go from red to yellow to green. And again, by the way, don't forget to pick up your 2 points of free credit, which is a substantial amount of free credit when you think of the weight attached to exams versus quizzes or versus homework. Labs are worth quite a bit, but let me get this quiz ready. Chapter 23, quiz 1. The other thing I like about that traffic light report is it's actually the most economical way to spend your time. If your goal is to spend as little time as possible prepping for exam 2, that traffic light report is the path. That is the way to spend as little time as possible and yet do well. All right. So chapter 23, quiz 1. Chapter 23, quiz 1. Oh, wait a minute. It is now 8:16. Okay, you should see it now. Please let me know if you can't, in case I'm screwing things up. You should see chapter 23, quiz 1, and it should look like this. Okay, our very first Gauss's law problem. The assumption is you have a good digestion, or at least an initial digestion of the lecture video for this. And this chapter 23 is quite heavy in terms of visuals and concepts, which explains why the video was also pretty heavy on visuals and concepts. Let me just remind myself what that was looking like. It was this one. Chapter 23, yeah. Lots of visuals, lots of drawing. For those of you who like to doodle and draw, this is a good chapter for you. I'm looking for those of you reading Korean. All right. So anyway, just wanted to kind of refresh myself. That was, again, lots of visuals, lots of conceptual stuff. And it's the underpinning. Again, I do remember from the lecture videos, Gauss's law is actually sort of integral to many different areas of science and engineering. So you're going to learn it here, and there's a very good chance you'll reapply it in similar and maybe even in different application areas. All right, so let's get started with our very first Gauss's law problem. We have a photocopying, the drum of a photocopying machine has a length of 48 centimeters and a diameter of 11 centimeters. This is what a photocopier drum looks like. So right there, we could buy this on Amazon right now for $34.99. This is a photocopier drum that you find inside of a Xerox machine. And this
we're still seeing the Microsoft.
Okay, give me 1 minute. There you go. This is a photocopier drum that you find in a Xerox machine. So again, this is what you could buy. And I think I did actually get this image from Amazon. So $34, $35. And this is at the heart of why you're able to make electronically reproduced copies or Xerox. Xerox, remember, Xerox doesn't like you to say Xerox because it's a trade name, but if we'll assume they're not listening to this conversation. This is what's inside of a Xerox machine, a copying machine. And the and we know the dimensions, we know its diameter, we know its length, the electric field just above the surface. All right, so let's do the first thing. Lots of drawing going on here. So let's draw a drum. Let's draw a drum that looks like kind of like what I just showed. So there's the ends of the drum, and then here's the drum surface. So do your best to draw this stuff well, especially on the exam. Okay. Good enough. This is the drum. Maybe I should erase this because that looks, to me, this gives me a headache looking at it. Like, there, that makes my headache go away a little bit. There's the drum. We know the dimensions here. 48 centimeters in length, diameter of 11 centimeters. The electric field just above the surface of the charged drum has a magnitude of that. So this is what happens in these photocopying machines. This drum is given an electrical charge. So let's just draw a whole bunch of charges. So I'm going to draw, I guess I'm assuming it's given some charge. So it's basically charged up. You guys maybe have done the thing. Have you ever taken like an object and, well, have you ever taken a sweater out of a dryer and there's all that static electricity and you can literally hear it crackle because you have that discharging. So for whatever reason, when a sweater or a piece of clothing made of certain materials is tossed in a dryer and it's being, tossed around inside the dryer, it becomes electrically charged. So now I have an electrically charged photocopier drum, and these remember the convention. If you're a positive charge, the electric field emanates or radiates from you in all directions. That is the convention, just to remind. Okay, so I have electric field lines emanating from these positive charges in all directions. So let's draw a bunch of those electric field lines. And this will be a little bit difficult maybe. So I have an electric field line going like that and like that. So I'm not going to draw all of these, but the point is, if I have charges on this drum, which is inside of your Xerox machine, I do have some electric field lines. And again, I'm not going to draw all of them, maybe just a few samples. Maybe like that. Okay. So maybe just enough to give like a 3D sense of what's happening. So it looks like, pins, like it almost looks like a cylindrical pin cushion, and these are pins just kind of stuck in, but hopefully that's enough. They're just going outward in all directions. Maybe I should do it like this for these guys. Let me change that. So this is the electric field that's surrounding this drum inside of your Xerox machine. Maybe these would be like that. Okay, so I think hopefully you get the point. All right. So, and et cetera, et cetera, et cetera. All right. What is the total charge on the drum? So that's the dollar sign. Step number one. What is the charge on the drum? So that's Q equals dollar sign, the charge on the drum. We have to figure out how much charge to give this drum so that it makes copies for us. That is the $sign, the charge on the drum. And I'm drawing a few sample charges and a few electric field lines. So this would be, maybe I can even call this electric field vector. These are all electric field vectors, and these are all little sub Qs. These are like, this is maybe Q1, this is Q2, Q3, so on and so forth. So the point is, what is the total charge on that drum? That's what we're after. So let's start with Gauss's law. Here's Gauss's law. Gauss's law is the integral of E, and I'll do it like that, E dot dA equals the amount of enclosed charge over the permittivity of free space. So I must have spent 20 minutes in the lecture video stepping you through every little bit and piece of the background story associated with Gauss's law. It's one of these cornerstones. In the world of electricity and electromagnetics, Gauss's law is definitely a cornerstone. So that's why so much time was spent talking through it in the lecture video. Again, with no prior knowledge was assumed. So I definitely went to square zero. So you have to have that understanding starting at square zero and ending up where we are now to really get the most out of it, to be able to be the best type of problem solver. So now I'm just going to keep hammering on this. Go to, this thing here. This means closed loop, closed surface integral. So this is what's known as a surface integral. Okay. So that's what, when you see this little circle, it means we're dealing with a surface here. And you would say, yes, of course, I can see I'm dealing with a surface because this is a differential surface element. So I'm just going to keep repeating bits and pieces like that over and over again. So I'm going to switch to magnitude angle. Switch to magnitude angle format. So the assumption here, and this has to be a good assumption, you guys have to be proficient with dot product, because here's the dot product. Here's vector A dotted with vector B. This is exactly equivalent to the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. So whenever you see this theta here, this theta is referring to the angle between vector A and vector B, these two vectors. That's what that theta refers to. And again, you have to be proficient. And if you're not, here's the good news is, I mean, there is never a hopeless situation. It's not like I'm saying, if you're not familiar with dot product, you're going to have to leave now. I'm just saying, if you're not familiar with the dot product, you need to get familiar with dot product. And there's ample resources. There's ample review resources. But this is this whole dot product thing. Dot product is the product of parallels. So we are interested in the parallel relationship between these two vectors. Dot product is product of parallels. That's like the mnemonic. Product of parallels. Okay. So this is why I switched from, this is why I'm going to switch from dot product. This is dot product form. E dot product dA. This is dot product form. I'm going to not change it. I'm just going to go to magnitude angle form. So ready? It's the magnitude of vector E, the magnitude of that differential element A, cosine of the angle between them. So this is just me instinctively saying, what is theta? Theta is the angle between that vector and this vector. All right, so that's the only change I'm going to do from, the only change I do from step 2 to step 4 is I just go from dot product representation to magnitude angle representation, Q enclosed. And sometimes I'm not 100% consistent. Sometimes I'll just refer to this as Q inside or Q enclosed over epsilon naught. Okay, so then let's say something about theta. What does theta equal? Theta is, again, the angle between DA and E. Theta is it's always the same, no matter what. It doesn't have anything to do with chapter 23. It's a dot product thing. What's the vector between, what's the angle between these two vectors? Let me just pick off a sample. I'm going to just identify a little tiny sample, a representative example right here, for example. For example, this sample. All right, so there is my differential. This is this is a surface patch. So tough to draw. All right, so this is a little sample surface patch, because if you remember, Gauss's law has to do with flux, and flux is how much is the density of electric field lines going through a surface. All right, so this has a name. This is my sample surface patch. Just drawing it as a visual aid. That's their sample surface patch. It has a name. The name of it is differential area. Sample surface patch, it has a name, differential area. It has a surface normal, which was another big deal. I'm going to draw the surface normal. Here's the surface normal, right like that. Okay, so this yellow line is a vector. So this is actually my vector. This is surface normal dA. That looks good, pretty good. So what can we say about that surface normal dA vector? A few things. We can say that it's perpendicular to surface element. That's what it means to be normal. Normal is just another word for perpendicular to. It's perpendicular to surface element dA. So I need to indicate that, yeah, for sure, this is perpendicular. So this orange vector is perpendicular to that surface area dA. So that is a requirement. The other thing I can say about dA, the magnitude of dA, which I can write like this, or I could just write it like that. The magnitude of dA is equal to the size of surface element dA. Because remember what a vector is. Vector is a magnitude and direction, surface element dA. So there, I am completely good to go for my surface element dA, my dA vector, which is one of the two vectors. Here's the other vector, E, right here. Okay. So this is what the dot product wants me to do. This is what Gauss's law by the dot product wants me to do. What is the angle between this surface normal vector and this associated electric field vector? This is the electric field that's piercing this sample surface patch dA. All right, and the answer is 0. You can see they're lined up, they're parallel. So theta equals 0, which is easy to process. All right, so theta equals 0 degrees because this electric field vector and that surface normal vector are everywhere perpendicular. So what I just spent 5 minutes going through with these two surface vectors right here, you would do the same thing a million more times. And no matter how many times you did, you'd always find out they're always the same. They're everywhere perpendicular. Perpendicular. Okay, so theta is 0. They're perpendicular everywhere because the electric field line radiates outward, emanates outward from every surface patch that's charged, or from every charge, I should say. So that's good. All right, number 6. So you know what? I'm going to leave off the little surface integral symbol. Well, I guess there's no reason. I was going to say to save time, but how much time does that really save? All right, so here we go. I have E times dA. Cosine of 0 is 1, so that just becomes 1. equals my dollar sign. Q, the amount of charge enclosed by that Gaussian surface. And oh, we have to talk about Gaussian surface. So I got to kind of back up here. I'm going to draw a Gaussian surface. Like this, I suppose. All right, so here's going to be my Gaussian surface. It's going to look a lot like a cylinder because my object, if my charged object is a cylinder, my Gaussian surface is going to look a lot like a cylinder. And I'm going to just envelop. So think of it like this. I'm basically shrink wrapping. I'm taking a piece of clear plastic wrap, of saran wrap, of clear coating. I'm shrink wrapping a Gaussian surface on top of this photocopier drum. Okay, so that's what I'm trying to indicate right now with my blue highlighter. So I need to talk about my Gaussian surface. This is my Gaussian surface. This is my Gaussian surface. It looks like a cylinder because the underlying source charge is a cylinder. This is my Gaussian surface, right? This blue highlighted, and you might think, oh, that looks exactly like the cylindrical surface. And the answer is, yeah, it is, but it's imaginary. It's not real. This is just a imaginary construct, a conceptual construct, because of what Gauss's law says. Gauss's law says that whatever this is right here, whatever that the integral of E dot dA is, it equals this on this side, where this Q enclosed, this is the amount of charge. This is the amount of charge enclosed by the Gaussian surface. That's Gauss's law in general, enclosed by my Gaussian surface. So it's important to take a bit of time to think about what your Gaussian surface should look like. But this is Gauss's law. The integral of E dot dA is equal to the amount of charge enclosed by the Gaussian surface divided by epsilon naught, which is the permittivity of free space. We've seen this before. We were introduced to this in chapter 21, and we've used it in chapter 22 as well. All right, so there's a lot going on here. I'm just going to take a bit of a breather here and say, all right, did I define my Gaussian surface? I drew my Gaussian surface. That looks good. I draw a sample patch. I did that. Okay, here's my sample patch dA. So dA is a surface. dA is the name of this sample patch. So yeah, here's my sample patch. It has a name. I drew the surface normal to it. And then indicate the electric field. So really this could become a recipe. Show the electric field vector at this patch, for this patch. So this is actually a pretty good, probably should keep this for this patch. Now that I'm just writing things down, show the electric field vector for this patch, find theta, or find theta, the angle between those two vectors, find theta between the electric field vector and my surface normal vector. And then I guess that's it. And then that's where we are right now. That brings us to step 6. All of this has just been set up, careful setup. All right, so step 7, we can process this. All right, so step 7, says, well, E is constant. So you know what? My electric field is a constant. So I'm going to bring that out of the integram. And I should talk about that. E, the magnitude, I'll say this. The magnitude of the electric field, which I can write like that or like this, is constant everywhere. Constant for all surface patches. That's saying it well, I think. So no matter, like if I wanted to draw what's going on here with this surface patch, well, there's my E vector, and then my dA vector is going to be, again, this would be my dA vector like that, and they are still parallel. So, and the electric field, because of symmetry and uniformity, the electric field is constant, because that's a good thing to add too. Because of symmetry and uniformity. Symmetry and uniformity. All right. So I'm going to bring E, step 8. My electric field can come out of the integrand. I know the integral of dA. That's going to just equal, the integral of dA is just simply A. That's my whole left side of Gauss's law. Here's my right side. The charge enclosed by the Gaussian surface over epsilon naught. So let's go ahead. A, this is the area of a cylinder. Area of a cylinder. Because my Gaussian surface is a cylinder. This is my Gaussian surface. It's imaginary, and I'm just going to just reinforce that. This is a cylindrical Gaussian surface, because my underlying source charge is itself a cylinder. So I know how to do the area of a cylinder. The area of a cylinder is equal to 2 pi r. That's the circumference times L, where this is L right here, and that's given. This is L from there to there. That's the length of my cylinder, which is given. And then this circumference right here, if I'm basically going to take, I'm going to take the circumference 2 pi r and multiply them. If I take one of these circumferences and multiply them by, I stack them up and multiply by L, that is the surface area of my Gaussian surface. So number 10 says, solve for Q. The amount of charge enclosed in that Gaussian surface. So I'm going to get the amount of charge enclosed by my imaginary Gaussian surface is going to be permittivity of free space times E times A. And with numbers, it's going to equal the permittivity of free space, which is 8.85 times 10 to the minus 12. Let me just look up my here's our textbook. Let's just check that out right here, because I could figure out the units, but there it is. Coulombs over Newton meter squared. Coulomb squared over Newton meter squared. Okay. So here, coulombs squared over Newton's meter squared. This is the permittivity of free space, which was introduced to you in chapter 21, times the electric field. And we used, and there are devices you can get to measure the electric field strength. Mine is 3.1 e to the fifth. 3.1 e to the fifth newtons per coulomb. And here's the area of this Gaussian surface. It is 2 pi r. I'm going to move this whole thing over a bit. Okay. 2 pi r, which is the radius. I don't know the radius, but I know the diameter is 11 centimeters. So this would be 0.11 meters divided by 2. That's 2 pi r. 2 pi r times the length of the cylinder. And my cylinder has a length of 48 centimeters or 0.48 meters. And let me just come up for air before I go to the calculator. This is epsilon naught. This is E. This is 2 pi r. This is my circumference, C for circumference. And this is L, and C times L is the area. Okay, so let's see where this takes us. Okay. I agree. All right. So now we know. Now we know how much charge needs to be placed onto this drum so it has a sufficient electric field strength to make copies. It's 4.55 E 4.5508 e to the minus 7. I don't know. I should do dimensional analysis because that will be a good sanity check. So dimensional analysis says this Newton here, Newton cancels with Newton. I've got meter squared here, but then here's a meter, there's a meter. And then one of these coulombs cancels with that. So I do end up with coulombs, which is what I would expect. This is the amount of charge that your drum needs to possess so that its electric field is strong enough to make the kind of copies we like. Okay. It's our very first Gauss's law problem, but that's part A. Part B is B. The manufacturer wishes to produce a desktop version, meaning smaller. So apparently we're going to take this copier drum right here, and we need to make it smaller to fit on a desktop. Back in the days when people made copies, the manufacturer wishes to produce a desktop version of this machine. This requires making things smaller. So we're making the drum smaller. It's shorter and smaller diameter, but everything else has to stay the same, because if you don't maintain that electric field strength, this whole process doesn't work. So what's the new charge? What must the charge on this new drum be? Kind of interesting, kind of a non-intuitive result, but everything's going to be the same. So we can kind of recycle. Step 14 for part B, what's the new Q? What is the new charge that needs to be placed on the drum? So what can we reuse here? I think we can reuse everything. So let's reuse number 12. So here's the new number 12. You're going to have this drum in your desktop machine is still going to be equal, have the charge of equal to epsilon naught. So I'm just going to write down the symbols. That's the same. The electric field is the same. The area is going to be different. The circumference is going to be, well, I'm just going to write it like this and let you do that. So, all right, this is a constant, so that doesn't change. This has to have the same electric field value. Otherwise, the reproductive process doesn't work. And this is going to be different. So this is going to be whatever your new circumference is times whatever your new length is, and that is the area. And the weird thing, well, not weird, but the interesting thing is you actually have to give it a lower charge. You actually have to give it less charge. Aha. Requires less charge. And that's because we're kind of concerned about flux. If you have a smaller cylinder, things get denser, so you don't have to charge it as much, because that's what flux is. Flux is not just the electric field strength, it's the electric field strength going through a given surface. Aha, requires less charge. So that's a good conversation we could really launch into about why, again, do I have to charge this with a lesser amount of charge because it's smaller? And because my first thought was, it's going to require more charge. If I make it smaller, I got to increase the amount of charge. But the opposite is true because of what flux is. All right, so you guys can finish that up, and then I'll get ready for chapter 23, quiz 2. Which will be our second Gauss's law problem. Let's see how people are doing before we move on. That's chapter 23, quiz 1. A lot of people are done, but not everyone. So let me just say, let's see. Elgert, you're done. So is Mo, Roman, Chris, Dan, Luke, Stephen, Minghao. Other people are still working out here. Let me just interrupt you guys to understand what I just rambled on about. So you have to start to really make a different approach to understanding this solution on the screen right now, because this is what happened in the past. This is what happened in the past. Elder, Julia, Mo, Roman, Chris, Matt, Dan, Luke, Jordan, Olivia, etc. You guys were all getting like full credit on these quizzes, and yet not all of you, but some of you couldn't even start a very similar problem on the exam. So the credit for this quiz that I'm showing you right now, and let yourself continue to not learn what actually just happened. And that's where the traffic light report goes in. But I just want to start hammering it. You can't be happy with just collecting your free credit, because this is, I mean, let's be honest, you guys, I'm doing the thinking here, and you're hopefully learning from listening to me think out loud. And that's what didn't happen on exam 1. So you actually have to learn from listening to me think out loud, and then you have to practice and you have to master it yourself. So again, do things differently. So let's go on to chapter 23, quiz 2. Give me a minute to get that ready. Because normally I would say a lot of us have to take a different, or a lot of you students need to maybe take a different approach for exam 2, but I actually have to say this, all of you need to take a different approach for exam 2, which again, I'm actually enthusiastic about that, because there's no way you're not going to do a lot better unless The only way you don't do a lot better, and there's nothing I can do about this, but the only way you don't do a lot better is if you really don't care that much. And I can't do anything about that, obviously. All right, so let's do this. Our second Gauss's Law quiz, Chapter 23, Quiz 2. Chapter 23, Quiz 2 is available. It should look like this. And you know what you guys can do. Again, this happens a lot in the other sections. Feel free to interrupt and ask questions. That's another kind of unique thing about this section. There's almost pretty much zero questions, which I get it. I'm not trying to hammer that too hard, because if you're like me, you won't have questions until you start to review a few times. So, but feel free, try to ask some questions. All right, so here we have a section of a conducting rod. All right, so this is pretty interesting. Let me just show this. A lot of times, I think everyone here has seen a picture like this, coax cable. This is, again, brought to you by our lecture video. I think pretty much all of you have seen this type of cable that looks kind of like this. Oh, look, from Amazon. So it looks like this. And this has a name. This is a coaxial cable. And everything has a name here. There's a lot going on. There's actually a lot going on with this cable. But you've seen these cables before. Broadband cable, coaxial cable. These are kind of everywhere. And that's kind of what we have here. Not exactly, but it's kind of what we have here. This is, you could say it's coaxial, meaning that there are two charged objects that are sharing the same axis. Sharing the same axis means coaxial. So if we do the read through here, this says the figure is a section of a conducting rod. Conducting, that's important. It's a conducting rod with we know a whole bunch of geometry about it. And then we know there's a charge. There's a certain amount of charge given to this inner conductor. So I'm just going to draw a bunch of little positive charges on the surface of this conductor to try to convey the fact that this inner conductor is positively charged, little positive charges, and it's positively charged by that much. The outer shell, which is also, again, it's coaxial, sharing the same axis. This actually is negatively charged. I'm just going to draw maybe a bunch of negative charges, negative, to show that, yes, okay, this is negatively charged. The inner shell is positively charged. Great. So, and I know the value of Q1. I know the value of Q2. Here's Q1. It's given. Here's Q2. Q2 is some multiple of Q1. So the first question is, what's the electric field? Basically, they're saying, number one, what's the electric field at R equals 2.15 R2? That's the question. All right, so this is where we hire Probert. Remember Probert. Probert is our hired field engineer. So Probert is sort of the name I give to a test charge. This is a test charge. So Probert is a test charge. The charge on Probert is positive one fundamental charge unit, which you could basically think of as positive 1.6 E minus 19th coulombs. And that's Probert. And again, Probert is a passive observer in this case. Probert's job is just to report. Let me not write passive observer. Probert's job is to report on the following. Probert tells us what's going on with the electric field force, what's going on with the electric field strength, and maybe some other things. I think right now that's it. Probert is just doing this in terms of magnitude and direction. So that's why we hire Probert, is to report on the magnitude and direction of the electrostatic force and the electric field. Okay, so Probert is standing off it at 2.15 times R2. So here's where Probert's standing, right here. I got to go out. I'm going to go out radially from the center. And there's Probert. Probert will be standing right here. Probert there. Okay, so let's label Probert. This is Probert. This is where Probert is standing. Probert is standing at R equals 2.15 times R2. So outside, the Probert's out there somewhere. Okay, so the question is, what's the electric field? What's the electric field vector here? That's the $sign right now. All right, so I'm going to make another drawing. I'm going to make, let me do like a face on drawing of our setup here. So here's the interconductor. So I'm looking at it like face directly face on. So this is my interconductor Q1. So here's Q1. It's the same setup. There's Q1, and then here's my outer shell. My outer shell is Q2, like that. Let me move it. Okay, so that's Q1. This is Q2. Q1, Q2. Okay, so it's the same thing, just a different view. And Probert is standing out here. Probert is now standing. I'll just draw Probert right there. Okay, and this is my distance. This is my 2.15 R2. So again, lots of good drawing stuff. All right, this is, I'm going to call this R subscript G. R subscript G equals 2.15 R2. That's a given. All right, so now it's time to draw my Gaussian surface. So step 2, draw Gaussian surface. And the question is, and this is where the thought process comes in, draw a Gaussian surface. What should my Gaussian surface look like? And the answer is use cylindrical symmetry, which is one of the 3 basic symmetries that we're going to deal with. Use cylindrical symmetry. Okay, so why am I using cylindrical symmetry? Because basically these are cylinders. My source charges are cylinders. So this outer shell is a cylinder and this inner charge rod, they're both cylinders. So it only makes sense to use cylindrical surface, a cylindrical symmetry for my imaginary Gaussian surface. And I want to stress this again, draw the imaginary. So this is just fictitious. It's an imaginary Gaussian surface. That looks good. This is, again, a different view. So this is just face on face view. This is face view. This is just sort of like a perspective view. Okay, so it's time to draw my Gaussian surface. I'm going to draw my Gaussian surface to look like this. Let's see if it fits. Okay, a little bit bigger. Not bad, pretty close. Good enough. That's it. That's it. This is my, right here. This is my imaginary Gaussian surface. Why did I draw it? Why am I making it a cylinder? And again, it looks like a circle, but it's really a cylinder. This is my imaginary Gaussian surface. And it's a cylinder because my source charge is cylindrical. And it's the size it is because it is sized to fit Probert. That's putting it nicely. It is sized to fit Probert because you need to figure out what is the electric field right here. So Probert's going to stand right there. So I'm going to draw an imaginary Gaussian surface to fit Probert because, again, I need to know the electric field at this point. This electric field is my $sign. And it would be the same over here. Like what if Probert was standing over here or here? It's the same thing. So no matter where Probert stands on this Gaussian surface, the electric field is going to be the same. But I'm just keying on this particular highlighted position just to go forward. All right, that's that. And again, I won't be able to draw this too well, but if I was going to try to draw, this Gaussian surface over here, it'd look like a cylinder that is basically enveloping so that's not too terribly bad. It's certainly not great, but anyway, this is what it would look like if I try to draw it in 3/4 perspective. It's just another cylinder that is centered on my underlying source charge. And that's why I would draw it to look something like that, but just to avoid the clutter. But again, I'm drawing, this is a cylinder. This is a cylinder. It's a cylinder. It's a cylinder in cross section. This is what you're looking at. It is a cylinder shown in cross section. Okay. So now we can, I think, proceed. Again, these problems are all kind of, it's like the lab. It's like the lab we did on Thursday. 95% of the time is spent setting it up, and then 5% is actually spent on execution. And that does become a kind of a common theme. All right, that's it. Gauss's law. In many ways, the hard part's behind us. So let's start with Gauss's law. E dotted with dA equals the amount of enclosed charge Q inside over epsilon naught. This is Gauss's law. So I'm not even really thinking. I'm just sort of going into like robotic mode. This is, yeah, okay, that's Gauss's law. Starting there, and then we'll now it's time to get thoughtful. Here goes. Number 5. I guess I'm going to start to, well, I'm still, all right. Yeah, I guess I'm starting to be thoughtful. Let's go from dot product. Let's switch from dot product to magnitude angle form, which would mean this is magnitude of the electric field, magnitude of the surface normal, cosine of the angle between them. And that's equal to the amount of enclosed charge. Enclosed by what? Enclosed by the Gaussian surface. Okay. And I can say theta equals 0. But we got to show that because now I'll draw my little surface patch. I'm going to do the differential calculus thing and say, well, I just want to get a sense. Let's see. Here's my surface patch here. Again, showing it in cross section. So this is my surface patch. It has a name. dA is the surface patch. It has a surface normal. It's going like that. And normal means perpendicular to. So this is technically my surface normal vector. And surface normal vectors, a little convention here, surface normal vectors always point from in to out, always point from inside surface to outside the surface. Because you could say, well, I could flip this direction. It's still going to be normal, but that's the convention. Now, here's a question. what's going on with the electric field lines? The answer is I have no idea. The only thing I know is Q1 is positively charged. So I'm going to draw a whole bunch of electric field lines. So if Q1 is positively charged, then by convention, electric field lines emanate outward from a positive charge. So that's why I'm doing this. Positive charge is emanating outward in all direction from Q1. Q2 is negatively charged. So by convention, electric field lines flow into a negative charge. So I'm going to have to draw that like there. There's electric field going in like that, going in. So I'm telling you, this is a very visually rich topic. And I think you get that idea. But by convention, electric field lines flow into a negative object, into a negative charge, and out of a positive object or positive charge. And I think this makes my point. So I basically have these electric field lines, try this again, messing with each other. These electric field lines, and this is the electric field. These are the electric field lines due to charge 2. So I'll just call that E subscript 2. And these are the electric field lines due to charge 1. So maybe I'll just call this E1. And they're messing with each other. Okay, inside they reinforce. You can see if I'm inside Q2, check it out. Here's an orange vector that's going in the same direction as that green vector. However, if I'm beyond Q2, if I'm standing here, for example, right here, from Probert's point of view, Probert sees the following. Probert sees an outward electric field line from Q1. So Probert's saying, okay, well, here's what's going on from Q1. Yes, it's going out fine. But Probert's also seeing an electric field line going in the opposite direction due to Q2. So again, we have this interaction, or we have this overlapping of electric fields. So that's a good visual. But anyway, this is why I'm saying theta equals 0. Theta equals 0 right here. And you could argue, well, maybe theta is equal to 180. I don't know. That will come out. That will come out in the next few steps. But remember what this theta is referring to. This is referring to the angle. Theta is the angle between these two vectors right here. So I'm saying, and then this would be my dA vector. This is a lot going on, I know, which is why hopefully you're watching these recorded Zoom lectures more than once. All right, so this would be dA. So theta is equal to 0 or 180. I guess I'm drawing it as 0. Theta equals 0 because it's referring to the angle between my dA vector and my E1 vector. And you can say, well, what about E2? But again, that will come out in the wash. All right, so now let's solve. Let's solve. We are trying to solve for the electric field. All right, so E is a constant because of symmetry and uniformity. We're saying you can't just assume anything. You can't just assume that I'm going to be able to follow your work. So you have to explain because of symmetry and uniformity. First of all, is it symmetrical? Yes, it is. Everything, I mean, this is a cylinder, so a cylinder is certainly symmetrical. Is it uniform? Yeah, it is. They don't talk about how it's non-uniform. So we just assume it's uniformly charged. Coming up, there'll be situations where it's not uniformly charged. Because of symmetry and uniformity, E is constant. So you know what that means? No matter where Probert stands, Probert could stand here or here or here. No matter where Probert stands on this Gaussian surface, the electric field is going to be the same everywhere because the distance between Probert and the source charges remains constant. Probert is not getting any closer or any further away from these charged objects. So that's actually the better description about why E is constant. So if E is constant, I can bring it out of the integrand. So I have, here's my new number 5. New number 5 says, bring E out of the integrand. The integral, well, I'll do it like this. So we're left with this. So once again, we're just going to get EA. EA. That's the left side of Gauss's law. Here's the right side of Gauss's law. So we're ready to solve. We are ready to solve step 8. We need to find the electric field. So here's the electric field. The electric field, I'm just going to do this, at R equals 2.15 R2. And then I'm going to use this subscript here, RG. R subscript G is what I'll use for the radius of my Gaussian surface. Radius of my Gaussian surface. My imaginary Gaussian surface, which in this case is just a make-believe cylinder sized appropriately. R sub G is whatever that radius is. Okay, so here we go. E at that position, which is where Probert is standing, is going to be the amount of enclosed charge all over the area of this imaginary Gaussian surface times epsilon naught. And we just have to plug in numbers, but let me make a little note here. This is the surface area of my imaginary Gaussian surface. So I know I'm repeating this a lot, but it's difficult at first. That's what A is. It's the surface area of your imaginary Gaussian surface. All right, so let's go with numbers now. Here goes. What's Qn? Qn is the amount of charge enclosed by the Gaussian surface. So this is where your visuals come into play. Look at, here's my Gaussian surface. So again, this is my Gaussian surface. What's the total amount of charge enclosed by that Gaussian surface? It's Q1 plus Q2. My Gaussian surface is actually enclosing both of those source charges. What's the area of this imaginary Gaussian surface? It's the area of a cylinder is going to be 2 pi r times L. And specifically, it's going to be R subscript G. So, all right, so the area is going to be the circumference, 2 pi r subscript G, size to refer. This is the radius of my imaginary Gaussian surface times L. All right, so with numbers now, for me, Q1 is 3.68 E minus 12. 3.68 E minus 12 coulombs. Q2, so I'm going to do a plus. Q2 is actually a negative 2.17. So I'm going to do plus a minus 2.17 times Q1, 3.68 E minus 12 coulombs. But this is the total amount of enclosed charge. That's my numerator. That's the charge enclosed by my imaginary Gaussian surface divided by 2 pi. Here's my radius. Where's Probert? What's the size? What is the radius of this imaginary Gaussian surface? It is 2.15. Okay, it is 2.15 times R2. So this is 2.15 times R2. That's where Probert is standing. That is the radius of my imaginary Gaussian surface. R2 for me is 10.7 R1. 10.7 times R1. And R1 for me, yikes, is 1.3 millimeters. 1.3 e to the minus third meters. Good heavens, that's a lot. Divided by epsilon naught, which is 8.85 e minus 12 coulombs squared over newtons meters squared. All right, so that's it. That's my numerator. That's my denominator. I better sanity check here just because I'm uncertain. This is 2 pi. Well, all right, this 2 pi. All right. Except I forgot L. I'm glad I did this. I forgot L. The length of that cylinder. I got all I got is the circumference. 2 pi r. Yeah, so I forgot L. The length of the cylinder. So let me move this over. There. The length of my cylinder is 13.6. 13.6 meters. And that probably would have come out in the dimensional analysis, but all of this is 2 pi r. All right. And I need a parenthesis. Okay. All right. Let's see what the numbers say. 3.68. Quite the calculator workout. All right. E at that position, negative 0.19037 newtons per coulomb. So magnitude, the magnitude of this electric field for me, I'm going to drop the negative sign. Is that what they're wanting me to do? Yeah, because they just asked for the magnitude. The magnitude is just simply going to be 0.19037 newtons per coulomb. I'll let you do the dimensional analysis. Direction is inward. Direction inward. So that answers the question, who won the war? Who won the war between charge 1 and charge 2? This negative sign right here tells you it's inward. And even maybe even better than that. As soon as you said that Q1 plus Q2 is less than 0, because Q1 and Q2 is less than 0, then the net enclosed charge is negative. Net enclosed charge is negative, and by convention, electric field lines flow into a negative source charge. So that if the net charge is negative, flows inward. E field flows inward. Okay. Oh, but there's quite a bit more. Let's see. What's our time check here? We'll take a good long. I'm going to keep just plowing forward with this, and then we'll take a good long break. I don't want to stop now, just to take advantage of momentum. especially since I think it does get easier going forward. So now what if Probert goes standing somewhere else? All right, so Probert's going to move from the outside of Q2 to just between Q1 and Q2. So part C says, what's going on when Probert is standing between Q1 and Q2? So I'm gonna wipe away a lot of this stuff here to clear the deck a bit. Otherwise, it's going to get too messy. All right, so we know about all of these electric field lines. This is going to take a while. Maybe not. All right, so maybe I won't delete everything, just Probert now. So let me hire a new Probert. Probert is going to go standing. Let me get a different pen. I'm hiring a new Probert. It's going to be that color. Okay. So Probert now is standing here, right there. And let me get rid of some more of this clutter. So this actually becomes easier. It's the same thing. It's the same approach. I'm going to use cylindrical symmetry, but Q1 is the only enclosed charge. Okay, so here's my new position. The location of Probert is here. Here's where Probert's standing, right there. Okay, so I'm going to call that, this is my new R subscript G. This is the radius of my updated Gaussian cylinder. I am once again going to use a Gaussian cylinder, an imaginary Gaussian cylinder as my surface. So maybe I'll just reuse this and scale it down and reuse this right there. Okay, so I'm just shrinking my Gaussian surface because I need to size my Gaussian surface so that it's encountering Probert. So that's lined up with Probert. It fits Probert. That's the way to put it. There. Good enough. Okay. This is my new Gaussian surface. Just make a little note about that. New Gaussian cylinder. Okay, so then maybe I'll start fast tracking a bit here because I can say step number 10 at R, which is now what I'm going to call again my Gaussian cylinder radius. Anywhere at that point, which is specifically 5.03 for me. My updated cylinder has a radius of 5.03 R1. And so I'm drawing it in cross section. It's really another, again, it's still a three-dimensional cylinder, but I'm not going to attempt to draw it in that view because it's messy. But let's go. Here goes. I have everything's the same. I have Gauss's law. I'm going to go just right to magnitude angle and QN. So this is just knee-jerk reaction, Gauss's law, not really thinking about it, other than I'm just starting off in magnitude angle format. This is what an electric field line looks like right here at a chosen point. So where Probert's standing, Probert is definitely encountering an electric field going outward because Q1 is a positive source charge. And the little surface normal looks the same way. This is dA. That's dA. There are my two vectors. This would be my little surface patch. Looks like that, perpendicular. Okay, so this we can kind of fast track this. Let's solve for E. E is constant everywhere for the aforementioned reason. So the integral of dA is A equals Qn. What's the total amount of Qn? What the total amount of enclosed charge? It's just Q1. That's it. Over epsilon naught. Number 13, solve for E. Solve for E. All right. Do you know the value of A? Let me just do a sanity check. Yes, I do know the value of A. It's the circumference 2 pi times RG. Do I know RG? Yeah, I do. It's this value. So, okay, I'm good with that. Do I know Q1? Yeah, it's given. Q1 is given. And then be done with it. Okay, let's solve for E. Let's solve for E for this case. We know it's going to be outward. My drawing shows that it's outward. So we just answered part D. Here's part C. Q1, 3.68, E minus 12. Don't forget L. I almost forgot L, the length of that cylinder. That's part of the area calculation. Okay. So here's the answer to part D, outward. I'm showing visually that, yes, the electric field in part D is outward. So let's do this. This is the answer to part C. This is part C. This is part D. Thanks to my very precisely drawn visuals. And then we got the answer to part A and part B. So it's now 9:34. I will see you. And we're back. That was quiz 2. Quiz 3.
I had a question.
Yep.
How did you find what F was on quiz 2? I'm still having trouble on that.
No, you're right. You're right. I forgot about that. All right, so let's finish that quiz. Okay, so this is getting quite messy, but this is all the work with exhaustive explanation that goes into A, B, C, and D. E says, what's the charge on the interior surface? Okay, so I'm going to reuse this visual here. Okay, so getting rid of the clutter. All right, so what is the charge on the inner surface? That's part E. Q1 itself is positively charged. So let me and it's a conductor. So that word conductor actually is important. Because it's a conductor, all the charges live on the surface. So just remember, opposites attract, likes repel. So all of these positive charges that are sitting on Q1, they hate each other. And they want to be located as far away from each other as possible. So what are they going to do? Well, number one, they can move. They can move because Q1 is a conductor. It's not a non-conductor. That's a different conversation. But all of those charges spread out as far away from each other as possible because they hate each other. And they're going to attract an opposite, well, an equal number of negative charges. So that's going to be a negative charge on the surface. So each one of these positive charges is going to attract a negative charge because opposites attract. Okay, so that's the answer to part E. Part E is equal to the charge on Q1. So let me just make way for that. We got all of that stuff right. So I'm glad you asked, because again, it's one thing to look at my answer and say, oh, well, you can see that the answer to E is just the charge of Q1, but it's negative. And again, that, to a lesser dedicated student might just say, okay, well, I'll put that. I don't know why, but I got the right answer. Tee-hee. So I'm glad you did ask about that. So for part E, Q1 attracts Q1 amount of negative charge. So like a little short essay. Positive Q1 attracts Q1 amount of negative charge because of opposites attract. So that's why the answer is negative Q1 is what gets attracted to that inner surface. And that's going to be negative Q1 or negative 3.68 E minus 12. So now you know. And again, glad to see that you're not just punching in numbers without really thinking hard on the why and the how. All right, so part F, what does that leave for the outer surface? Outer surface, what's left? What's left? Because what's left? I have this much Q2. This much Q2 was attracted to the inner surface. Let me just write that down. This much Q2 fled or traveled to the inner surface. Traveled to inner surface. What does that leave? So what's left is this much. It's going to be Q2 minus the amount that fled or that traveled to the inner surface, which is the same as Q1. And that's the answer. Okay, so for me, it would be Q2, which would be 2.17 Q1 minus Q1. That's the leftover charge that has not fled to the inner surface. And so you know what it's going to do? It's going to travel. This amount of charge will travel to outer surface. Because again, they hate each other. These are all negative charges. They hate each other. So they're going to travel outward to here. So I'll draw that here. So interesting little scenario. I'm drawing the leftover charges that are going to be repelled by the negative charges on the inner surface. And that's that. Okay. All right. Time for quiz 3. Okay. Quiz 3 is now available. should look like this. I better get rid of this. Okay. Quiz 3. It's another cylinder, so we're definitely sticking with cylinders. We have to get to spheres. A lot of the spherical stuff is done in the deep dives, and let me just remind you guys that the deep dives are every bit as fair game as the stuff we're doing during Zoom class. So don't forget that a highly recommended lifeline would be these deep dives, and there's quite a few of them, I think, for chapter 23. There are. So this is why exam 1 wasn't easy. I shouldn't say exam 1 was easy, because that's sort of insulting. For those of you who actually learned the stuff well and did well on it, then that's insulting to say it's easy. But exam 1 was certainly reasonable if you prepared the way, you know, a typical engineering student prepares. The same is going to be true for exam 2. So don't forget to use these lifelines in addition to rewatching this lecture video that I'm recording as we speak, in addition to watching the recorded green sheet lecture. So might sound like a lot of time, but that's part of spending the least amount of time possible to do well. I don't want to spend any more time than I need, but I need to spend just the bare minimum to do well. So I have another long non-conducting. So this is not a conductor, it's a non-conductor. So here is, I'm going to take another stab at drawing my cylinder like this. Lots of drawing fun today. That's part of it. I mean, take care in drawing. I mean, for me, I spend time drawing this stuff. I try to draw it carefully, not because I'm an artist at heart, but because it helps me visualize. It helps me get my head screwed on straight. All right, so here's my long, non-conducting solid cylinder. We know that, here, this right here, you guys, and again, anticipate this. You know what I'm thinking right here? This is calculus. So as soon as I see non-uniform, I kind of have a little knee-jerk reaction, calculus. I mean, maybe not, but that's the safe assumption. Non-uniform means calculus. A non-uniform volume charge density, that is well, and they're actually telling you that here. Again, that is a function. All right, so that is a function. So again, calculus. Now, it could turn out it's not calculus, but I think it's wise for you to just be extra sensitive to the possible need of using calculus, because a lot of times you're supposed to use calculus, but you don't use calculus, and that it's tough to find a lot of partial credit in that situation. So even if you get the wrong answer, if you at least kind of know that this is a calculus approach, that's some healthy partial credit right there. All right, so we have non-uniform. This is a non-uniformly charged, non-conducting solid cylinder. A lot going on here. So those are all key words: non-uniform, non-conducting solid cylinder. So I'm just going to clear the clutter for a bit because I made my point, I think. All right. And now Probert's going to stand, I guess, for part A inside. Probert is actually going to go standing inside somewhere. Inside, maybe let's put Probert right here. Probert is standing inside, right there. Okay, and that defines the Gaussian surface. So if Probert is standing right there, I'm going to use that to define my Gaussian surface. I'm going to do my Gaussian surface right now. Here is my Gaussian surface, which will look like a it will look like a cylinder because my source charge is cylindrical. So I guess I'll just reuse the wrong color. All right, so more drawing fun. Here's going to be my Gaussian surface sized to fit Probert. I'll do that right there. Okay. So this Gaussian surface I'm drawing is not an actual real or physical surface. It's just imaginary. And it's sized again to fit Probert. So right here. Oh, look at that. Here's Probert. Probert, size to fit Probert means Probert is standing right there. Okay. Inside somewhere. That looks good. So this is my actual charged object. So this is real. This is real. This is my real object. And this is my imaginary Gaussian surface, my imaginary cylindrical Gaussian surface. Size to fit Probert. Sized to fit Probert, which is the point. Probert's standing at a point that we're interested in. So that's the whole function of Probert. It's to stand where we want Probert to stand because we're interested in that location. Size to fit Probert. All right, so let's go. Let's go. Here's well, I'll do the niceties. This is going to be my surface patch right there. This is going to be dA vector. And is this positively charged? Yeah, it's positively charged. How do I know it's positively charged? Because they give me right here. How do I know it's positively charged? They don't really say. So I guess I have to assume it's positively charged. We'll see if that's actually a factor. But this is my electric field vector and my surface normal. Those are the two vectors that you have to worry about. So this is my electric field vector. There's my surface normal vector. This is my surface patch. Surface patch is the patch through which I'm worried about flux. Okay, so number one, Gauss's law. Here's Gauss's law. Gauss's law, magnitude angle, E dA cos theta equals the amount of charge enclosed by the Gaussian surface over epsilon naught. Theta equals 0. Seems to always equal 0, but it won't always equal 0, but it has thus far. And theta equals 0 because theta is the angle between my dA vector, which I've drawn, and my electric field vector, which I've drawn. So I'm showing everything. The goal is not to leave anything to the imagination. It's going to be easier said than done, or it's going to be not as difficult as you might think right now because it's all new. But here goes. What is E? Well, first of all, what is Qn? What is the amount of enclosed charge? What is the amount of charge enclosed by my imaginary Gaussian surface? What is the amount of charge enclosed by my Gaussian surface? That's what that refers to. And this is where the heavy lifting is going to come in. And it won't be, I mean, it'll be heavy at first, but not after you digest it. The amount of charge enclosed by my Gaussian surface. So here we go. Rho, this is Greek letter rho. It's not P, it's Greek letter rho, is defined as charge per volume. So charge can be written macroscopically. It's the total amount of charge divided by the total amount of volume, but I actually have to differentialize it. So it's going to be dq over dv. I have to differentialize since it's non-uniform. Since rho is non-uniform, you got to use calculus. So again, you had a few triggers here. You had a couple of triggers here that nudged you into thinking calculus. Since rho is non-uniform, I need to differentialize. I need to use calculus. Okay, so this is why I'm saying my charge density is in fact charge per volume, but I'm differentializing it because I need to set up my integral. And that means this is the amount of enclosed charge. So ready. The amount of enclosed charge is going to equal the integral of dq, which now I can write as the integral of rho dv. That's my amount of closed charge. All right, and I guess let's worry about limits of integration. Let's talk about what we're doing here. Here's the radius of my charged object right here. There. All right, so that's the radius. So this is again my well, you know what this is? This is r sub g. This is the radius of my imaginary Gaussian surface. That Gaussian surface is enclosing how much charge? So I got to use calculus. So my limits of integration, I'm going to integrate. I need to go from the very center of that Gaussian surface, which is r equals 0, all the way to rg. And for part A, rg is equal to 1.5 centimeters, 0.015. Those are my limits of integration. Now, what do I do with dv? What's my differential volume? How do I handle that? I can't integrate this because that's not integratable. How do I handle differential volume? So this is what I'm going to do. I'm going to do a face-on view. So here's a face-on view of this imaginary Gaussian surface, just so it's going to be easier to draw. So this is the same Gaussian surface in cross sections. This is face-on, face view. Okay. So I guess the first thing, I'm going to do the calculus thing and say, well, I'm going to define a surface patch. Okay, so here's a surface patch. Make it a little bit bigger. Good enough. All right. So this, what's the area? What is the area of this surface patch? The surface patch area, and this is getting into the weeds a bit. This is kind of going down the rat hole, unless you've had this calculus, which I think you had to have. But anyway, actually, maybe I'll do it. Well, I'm going to do it the heavy way and then the light way. So here's the heavy way of figuring out what dV is. Okay. I need to figure out what is the area. What is this differential area right here? So I'm going to do it heavy and then light. What is that area that I'm cross-hatching right here? And the answer is, well, it's just going to be RD theta. Where did that come from? So it's going to be this. It's going to be this arc right here. This arc right here. I'm remembering birth of a radian. Birth of a radian says S equals R theta. And so ds equals R d theta. So this differential arc length is just going to be ds equals R d theta. How many of these arcs do I have? And the answer is I have this many arcs. This is one arc. And then I'm going to multiply them through by this dimension of this patch. And this is dr. So when I take dr, it kind of looks like it's a square. But if I take one of these arcs right here and multiply by dr of them, that's that differential area. So my differential area that's cross-hatched, that's shaded in red, is just going to equal r d theta times dr. Okay, so I'll draw that right here. This is my little differential surface area that I'm focusing on right now. It's just basically looking like that. Hard to draw like this, but there it is. It's sitting here right there. Good enough. All right. So this patch here is the same as this patch here. So now that I have one of those patches, I need to multiply it by all of the patches in this cross section. So what is this cross section right here? It's this. And then how many of these cross sections do I have? I have L of them. So that's dV. dV is going to equal this dA patch, which is right here. This is my little differential patch that I integrate to encompass this entire cross section. And believe me, I know your head might be spinning unless you've had this calculus before, but I don't, well, this is maybe just background. So I have this entire green shaded area, and then I'm going to multiply that green shaded area by L right here. And that's it. That is my differential volume. So dV equals dA. Here's dA, r d theta dr. This should have been dr. That's differential area times the entire length. Good to know. Theta, I need to get all 2 pi radians. So I'm going to integrate from here all the way around that circle. I'm going to integrate from 0 radians to 2 pi radians. So dV equals 2 pi r dr times L. All right. And 2 pi r is just the circumference. You could say, well, this is just the circumference. I'm going to take one of these circumferences and then multiply them outward until I get this entire surface area. That's a lot. Here's the 1/10 the effort. You know the volume of a cylinder. The volume of a cylinder is pi r squared, which is the volume, which is the area of the circle times L. So if the volume of a cylinder is pi r squared, because the cross section of a cylinder is a circle, this is the area of a circle. If I take the derivative of both sides, I get 2 pi r dr times L. So this just took 1/100th of the time. It gets you the same expression, but I don't think we should be happy with just kind of doing it. This is sort of like the unofficial method, or like, again, the very lightweight method. All right, so that's the heaviest part. That is the heaviest part of this conversation. Just my rambling about differential volume. All right, so here's Qn. Back to sanity. Qn is going to equal the cross, or the integral of rho. They gave you rho. And again, as soon as you're seeing that, you should think, well, you're thinking calculus because of this word, non-uniform, and this word function. But rho is what they say A, and that's not area. It's kind of a bad choice for a constant, but it's A r squared times dV. Here's dV. dV, after this long odyssey, is 2 pi r dr times L. So all of that is the amount of enclosed charge. Once we get done, this is rho. This is dV. And again, this careful with that. This is not referred to surface here. This is some constant A. And they give you A. They gave you A right here. A is some constant. So that's what it's referring to, a constant, not a surface area. But that's it. That's it. All we have to do is update our Gauss's law, number 6. Number 6 says, okay, let's update number 1. So here's our new Gauss's law. The integral of E, well, you know what? It's going to be the same thing. Updated number 1, it's going to be E times A, because all of this produces EA. So just in the name of fast tracking, you'd show the work, you'd show all of the work and steps just like we've done before, but we've done this a bunch of times already. So this is EA on the left side of Gauss's law equals the integral. So I'm going to do the integral of AR squared 2 pi R dr times L from 0 to where Probert is standing. Probert is standing at 0.015 meters from that central X. There's where Probert's standing. And all of this is Qn over epsilon naught. Okay, let's simplify things. So E times A, I'll do number 7. Let's talk about A. A is the surface area of this Gaussian surface. So once again, this is my Gaussian surface right here. It's not real. It's imaginary. It's size to fit Probert. What is the surface area of that Gaussian surface? It's going to be 2 pi R. I'm going to write it like this, RG, because this radius is in fact RG as indicated here. So it's going to be 2 pi R, 1 circumference times the length L. So collectively, when that term right there is my Gaussian surface area. This is the area of my Gaussian surface. Okay, that's the left side of Gauss's law. Here's the right side of Gauss's law. Equals, I'm going to bring all of the constants out of my integrand. So I have, what's constant? There's 2 pi L. So I'm going to bring 2 pi L, 2 pi L A. All of those are constants. 2 pi L times A, integral of R cubed dr all over epsilon naught. Okay, let me back up for a minute because this should be from 0 to RG all over. That's better. All right, and you can see the L's cancel. So let's just clear the clutter right now. That can cancel with that. And the 2 pi's can cancel. 2 pi R. Okay, I guess this is good. So this is getting very simple very quickly. All right, let's update. So number 8, E times RG equals 2 pi L's canceled on both sides. A, I'm not going to, A over epsilon naught times RG to the 4th over 4. because the integral of r cubed is r to the fourth over 4, and then I'm evaluating it. Okay, so is this the answer? Number 9. The electric field is going to equal A RG cubed all over 4 epsilon naught. Is this right? Well, you guys check, don't just passively write things down or just stare at me. I mean, sanity check me, because if there's ample opportunity to make mistakes. So let's try numbers. This number, A, this is some material constant. So you, as a materials engineer, would work with an electrical engineer, and you would actually formulate a material to have this A value. A equals 2E minus 6 microcoulombs. A microcoulomb is 2E minus, or a micro is 1 times 10 to the minus 6 over meters to the 5th. Okay, so with that in mind, that's what A is. 2E minus 6. Okay. All right. Heavy. That's what happens when Probert is standing inside. We can fast track part B. Let me just do some erasing here in case you're still catching up with stuff. Part B, I think, is easier than part A. That's part A. I actually get a little bit of variance between my number and the accepted number. My guess is because they didn't store all their intermediate values, which they normally do, but I'm definitely within 2%. Okay, so let me move some things around here. All right. Let me just carve out a little pocket for part B. All right. Part B. What if Probert is standing at R equals 5.2 centimeters, which is outside of the physical object? Because 5.2 centimeters is beyond 4.3 centimeters. Again, my numbers. So Probert now has moved to the exterior of the actual physical object. Probert is standing here somewhere. So that's my new Gaussian surface right there. So maybe I can repurpose this. Here's my new Gaussian surface. It gets a lot bigger. Let me get rid of this. Okay. my new Gaussian surface is bigger because it has to fit Probert. Good enough. Okay, so this new Gaussian surface has a different Gaussian radius. All of these earlier steps, we can just recycle those. Here's my new Gaussian radius. This is my new RG. Okay, so everything's the same. So what can we, for part B, if my new Gaussian surface, if the point I'm interested now is located at R equals 5.2 centimeters or 0.052 meters, what's my electric field at this point? So there's my updated visual. So what changes? Let's number one, here's Q. The total amount of enclosed charge is going to equal, everything's going to be the same here. So let me do this. Let's just recycle. Let's just recycle number 5, number 6. I'm gonna start with number 6 again. I could almost start with 7. I'll start with 6. So number 6, just to backtrack a bit, number 6 said that E times A equaled the amount of enclosed charge. So this is going to be from 0. And here's my new Gaussian surface from 0 to 0.052. And that's the only thing that changes, because then my integrand is going to be A R squared 2 pi R dr times L all over epsilon naught. Okay. And that's still going to be, here's the new number 7. The new number 7 was E times 2 pi R, the circumference of that Gaussian surface, times the length of that Gaussian surface, because that's area. All of this right here is area. That's the left side, equals on the right side, after processing it exactly the same way. That's it, from RQ to 0 to RG over epsilon naught. Okay, and then I guess we're done. Number 3 is the electric field is going to equal, well, it's the same thing, ARG cubed. Is it the same thing, just with, I guess so. Oh, oops, not quite. Yikes. That was dangerous. Here's my mistake. I got to go back to number 1 right here. Okay, so this was a mistake. All right, erase. I'm not integrating from, this is not my enclosed charge. My enclosed charge is contained from R equals 0 to R equals 4.3. So this should be 0.043. 0.043. Okay, so let me sanity check. This is the electric field, 2 pi. Yeah, this is the, I wish I could claim I made that mistake on purpose, but I didn't, but it's a good thing I did, because this is my Gaussian area. So this is a great opportunity to really talk about what's happening, what's truly happening. All of this is my Gaussian surface area. Over here, this whole thing, so this is my Gaussian surface area. All of this is my enclosed charge. This is the amount of charge enclosed by that Gaussian surface. So that's why I don't want to take the radius of that Gaussian surface. I want to take the radius of the physical object, which for me is 0.043. All right, so going from, which means this is good on the left side. That's going to be good. That is okay. But this is not RG. This is not RG. This is 0.043 with my numbers. This is 0.043. I'm getting rid of 3 altogether. Okay. So here's my left side. Number 3. Here's my left side. It's going to be E times 2 pi L RG, 2 pi L times RG, 2 pi L times RG. That's the left side. Here's my right side. My right side is going to be 2 pi LA over epsilon naught times, I guess I'll just throw it as a number, times 0.043 to the 4th over 4. That's it. So I still can cancel some stuff out. 2 pi here cancels with 2 pi here. L cancels. Okay, so I am left with the following. My electric field at this new location is E. The electric field is going to be equal to A all over 4 epsilon naught RG times 0.043 meters to the 4th. And let me sanity check that. If I did 3 correct, E equals A over 4 epsilon naught. I think that's right. Okay. Where RG is referring to the Gaussian surface, not the physical object. So this is where you have the 0.052. Okay, let's see what that does. Okay. All right. see how everyone's doing. Great check. Yeah. I mean, a lot of people are done. A lot of people aren't. So maybe I need to, I'll wait. I'll try to take some more time, finish this up. And again, I should just record the following and play it on a loop. Do more than just get the right answer. Subliminal learning. Just listen to the sound of my voice saying, do more than just get the right answer.